So last class, we looked into the addressing modes and yeah, so there are many multiple modes. So in that, we have 5 to 6 important modes, right? In and there are 8 important modes. In that, 5 to 6 are very important. So the first one is the base relative addressing mode, um, where the B register or the B flag, right? So last class I told you that we have 6 flags, NIX BP, 6 flags. N is for direct, I is for indirect, X is for index, P is for base, PC, and extra. So we have 6 types of flags. So here, for different addressing modes, these flags will change. So for base relative addressing mode, my B flag will be 1, P will be 0. And for program counter, this is just opposite. Okay. So if it is B, it will not be P. If it is P, it will not be P. So how do we calculate the target address? The target address for when B is equals to 1 is the contents of base register plus the displacement will actually give me the target address. So program counter, which is also called as relative, where the P flag is 1, B is 0. The target address is nothing but the contents of P plus the displacement. So PC register contents. Yes. So direct addressing is, so in direct addressing, P will also be 0, P will also be 0. So in other words, the target address is displacement itself. We do not have any contents which should be added. So format 3 allo aste, format 4 allo aste. So next comes the base relative index addressing mode. So as it says base relative, B will also be 1 and the index which is X will also be 1. So here the target address is base plus index plus displacement. Next, program relative index addressing refers to, this is ulta I told you. B is 1, P is 0 in base relative, P in 1 and B is 0 in program relative. Right? And as it is index, X is also equal to 1. The target address is contents of PC register, contents of index register plus the displacement will be the target address. Next, immediate is where I is 0, I is 1, N is 0. Immediate. I stands for immediate addressing. I is 1 and N is 0. So target address is equals to target address itself used as operand. Whatever the target address here, all immediate addressing will have a hash symbol. That hash is nothing but hash itself is the value. You don't have address here. The operand value will be the straight away the address. So no memory reference for immediate addressing. So next comes the N. If N is 1, then it is indirect addressing. If N is 1, indirect addressing. So here, the target address will be equal to the displacement value, same. So simple addressing is where either I and N are 0 or I and N are both are 1. Basically, the target address, again, it is the location of operand, whatever you have. So for format 3, in base relative, displacement is interpreted as 12-bit unsigned integer. In PC relative, displacement is interpreted as 12-bit signed integer. Right? So this is what you need to understand here. As I told you, hash refers to immediate, at refers to indirect, plus refers to it's a 4-byte instruction. The star refers to it's a current value of PC register. C stands for it's a character. Okay, so when you have X anywhere, then it says that it is an index register. So base B stands for base register. These are the symbols, special symbols which are used. Next is, I told you for immediate, I will be 1, N will be 0. For indirect, N will be 1, I will be 0. Okay. So for index, X will be 1. So always remember B and P both cannot be 1, either base or program. Both can be 0, but both cannot be 1. So here we have a example how to generate the object code. Yeah, individually we can see below, right? So this is the address 3030. So these are the memory address. These are the contents. Okay. I'll explain you about this complete opcode individually. Yeah. So next comes the instruction set. So we are speaking about the instruction set of SIC-XC, extended version of SIC. So in the instruction set, we have load and store instructions. LDA meaning load into accumulator, load into index, store into accumulator, store into index. Okay. Load to base register, store to base register. These are the load and store instructions. When it comes to the arithmetic instructions, SIC supports floating point values. SIC doesn't support floating point. So here we have the arithmetic operations of add, sub, multiplication, division. Apart from this, you can also add the floating point. If you are adding the floating point values, you should use addf, subf, mulf, and divf. Here F stands for floating. There is a difference between a normal and floating point because we see that some more bits are actually assigned for floating point. Next, register move instructions moving towards the register, right? So where both the operands are actually registers. Moving the contents of one register to another register is where register move instructions specify. So if one register to another register, you add, subtract, multiplication, and division. A special purpose registers, a special supervisor call SVC instruction is provided. And yeah, this with respect to the interrupts. Next, comparison instruction. Compare with the given values, compare with the registers, and compare with the floating point registers. That's what it says. Conditional jump. This is like your if condition. If the condition is lesser than, greater than, and equal to, it will be moving to one instruction to another instruction. JLT stands for jump if lesser than. JEQ refers to jump if equal to. JGT stands for jump if greater than. Subroutine. Subroutine linkage instruction refers to from one function to another function and coming back to the same function. So how do you move from one function to another function? JSub, jump to subroutine. RSub refers to return from the subroutine. So next is input and output. I told you that there will be a conditional code which will be giving me the status, whether the device is ready or not. Right? So input and output is performed by transferring at a time one byte of data from one register to another register, or one register to the device, right? So most of the time, at a time, from the rightmost 8 bits of the register accumulator. So whatever you want to push towards the memory space for the output, it should go through the register only, accumulator register. So each device is assigned a unique 8-bit code. Each device refers to, it can be any memory device. It can be a storage device, right? I'm sending data from one place to another place. So at a time, we actually see 8-bit code, which will be, the device name is given with 8-bit code. 8-bit code refers to, we have 2 characters which can be set to the device. 2 characters starting from 00 to FF. So these many characters you can actually give 00, 01, 02, 03. Similarly, F0, F1, F2, F3, FA, FB, FE, FC, FD, and FF. So we can assign more number of devices. 3 IO instruction which specifies the device code as operand. So first is whenever before reading and writing, you have to test the device whether it is working fine or not. So how do we do that? Using the TD instruction. So TD stands for test device. So test device is very simple. It is checking whether the device is ready or not. So how do I get to know? If the test device is lesser than the value, then it says that the device is ready to send the or receive. If the test device value, if it is equal to, then the device is not ready. So what are the conditions what we need to do if the device is ready? So test continues unless the device is ready, right? What happens when it is not ready? It will be repetitively checking for the device to get ready. For every second or millisecond, it will be checking whether the device is ready or not ready or not ready or not. Once the device is ready, now, yes, we can do either two things. One is read and the other one is write, right? Once ready, when we deal with the reading of data, meaning from the device to the register. So from the device, the data will be pushed towards the A register. Always accumulator is accumulates, get it? That's why it is given as A. A. So transfer the data from input device or keyboard to rightmost byte of the register A and stored in buffer if required. Why do we need to store in buffer? Sometimes the device is slow. Sometimes the device is slow, right? Sometimes the register may not be available at that time. So the data will come and fall in the buffer for some time, unless until the register is ready, right? So if required, so the read index and the storing the data. So indev refers to the input device. Read from the input device and store into accumulator to from the data. So read index antakshna, index value will be stored into accumulator. From here, what are you doing? From accumulator to data memory space, you are pushing it. So this is the reading, read from the device. Next, the other option is write. So when you want to use, when you want to write the data from the memory device to the output device, right? It cannot go from memory device to output device straight away. Accumulator will again come into picture, meaning the processor will only be able to push the data. So write data. So here a byte of data is loaded. Every time a byte, meaning 8 bits, will be loaded into the accumulator from the memory to accumulator, and from accumulator to the output device. So at the rightmost byte of register A and then return to the address device, that is LDA from the data, because data is where my values are present. From the data, get it to the accumulator register and write it into the output device. Right? So this will do the job. So there are I/O channels that can be used to perform input and output while the CPU is executing other instructions. So what do you mean by this? Your writing and reading can be done in the background via the channels. The CPU can be executing or it can give its time to work on something else. So the CPU is executing other instructions. This allows overlapping of the computing and I/O, resulting more efficient system operation. So SIO is nothing but starting of the I/O channels. So TIO refers to, yeah, so to test, the I/O, and HIO starts for halt the I/O. So by using these particular value, you can actually deal with the problem. So next is about the programs. So this is where you need to look into give some time clearly, because these are important and your question paper will have one problem on this. So SIC XE programs, right? Not much difference between SIC and SIC XE. SIC is 3-byte instruction. SIC XE is 4-byte instruction. Meaning I have extra 8 bits to deal with. 8 bits or 1 byte. So LDA, what does this hash refers to? It is immediate value, which is 5. So loads value 5 into register A. STA alpha. From the accumulator register, push it into alpha. Meaning loading this 5 value is putting to alpha. Okay. You got the immediate value to A and A to alpha you are pushing. Next, load into immediate value 90. Load the ASCII code for the value into A. So what will be the ASCII value for 67 is capital A. Yeah, let's see. Maybe it is into A. So let's 19 ASCII character. Yes, it is Z. Okay. So it is Z here. This value is actually Z. So the ASCII value Z will be pushed into the value of A and store that character into C1. So Z will be sent to C1. So here we have to specify what is alpha, what is C1. Alpha is actually a reserve word, which is 1, right? And what about this C1? C1 is a byte. So C1 is a reserved byte, which is also having 1 byte information, and this is 1 word. Here we should know that 1 word is actually equal to 3 bytes. Okay. So next comes the arithmetic operation, how the plus and minus will be dealt. So S is a special purpose register where S can be used. So LDS, load into S, what do you have in INCR, right? So the INCR will have 1 usually. So LDS is this NCR is actually added to special register S. Load into accumulator from alpha. What do we have in alpha? We do not know. See, those are the information which should be given, right? So load the value of alpha to A. What is the value of alpha? You have not specified. But this is how these are the examples how it looks. So add into register S and A. S and A from so again S value will be added to A. A which is having the older value, which adds the value of S and stores in A only. So A will be equal to A plus S. That's what it says. Next, sub meaning in my register A, decrement 1 and save it in A. And that A value store it in beta. This is how the arithmetic operation. Looping actually works in this way. So looping and index operations. So gamma is equals to alpha plus beta, meaning what is alpha and beta? They are the array of 100 words each. Meaning 100 words refers to 100 into 3, that is 300 bytes. So these are the examples. Probably, I think it should be seen individually. So LDS immediate value 3, LDT immediate value 300, LDX 0, right? So this is actually an algorithm which actually tells to loop. Okay. So we have the add loop here, right? So here the looping happens from here to here. Okay. So in the loop we actually discuss. So we'll take that again because we'll look into the concepts first. So in your exam, they may ask one question: simulate arithmetic operation using assembly code. Then you need to write this. Okay. So it can be arithmetic operation. It can be a data movement. It can also be this movement of TD, read and write, right? So always be ready with few things, how exactly it works. So here he is telling that to read 1 byte of data from the device F1 and copies to device 05. So how do I getting the data? How am I saving the data? In loop and out loop, right? So these are the programs. So these are all the example programs which is given. So subroutine call to read 100 byte records from an input device. So 100 times you are getting from the input device, right? So these are the examples. So we'll take in the examples once. We'll understand how to write those. Okay. So next is sequence of instructions for SIC to set the alpha equal to the product. Again, this is also a problem. This is a program. We actually see many programs here, and we have 11. Over.